Okay, all right. I think we're gonna pick up where we left off here. We all are settled. So just to finish off the previous topic, I'll just mention a few challenges that are typically associated with running these SSO studies. First one here is detailed system modeling. So we need our system model to include accurate representation of the series compensation and frequency-dependent transmission line models. And the series compensation in particular, it's not just, you're not only worried about the value of the capacitor, there's a fair bit of associated protection logic for those series capacitors that you often need to put in the model as well. So there'll be surge arresters across the series capacitor, and there'll be bypass switches, and there'll be some other things like sometimes there's like a triggered air gap and things like that, which are necessary to stop the rapid buildup of voltage across the series cap when there's a nearby fault. So there's some modeling details there we need to get for the capacitor itself. And we would get that from the capacitor manufacturer or whoever is installing that other protection equipment. We need the accurate EMT models of the IVRs consistent with actual field firmware. So this is one in particular where a generic model is not going to give you at all the right frequency characteristic of the IVR. So it's very important that all of those modeling requirements they talked about yesterday are in the model. And these SSCI studies are actually what a lot of those accuracy requirements originally came out of, because we determined that we basically couldn't study these issues like at all. They were useless to do with generic models that didn't represent the actual facilities. So this was actually one of the main drivers for those requirements years ago. Synchronous machine shaft modeling, so torsional models with mechanical damping data along with the SN curves are nearly impossible to get from the manufacturers. So sometimes these studies are, like as you can see, like for screening wise and for the stability studies, you'd really need this torsional data to do an SSTI or an SSR or an SSTI TA study. But that data is really hard to get so that's, I guess, a note to require that data from those generators and make them aware that if they're in a series compensated system, that they may be required to produce that data, or if they're connecting nearby IVRs or loads. So stakeholder coordination is really a large challenge when it comes to data transfer as well. There's utilities, ISOs, and GOs involved, and you need to get that model or that data through all those entities to the consultant or whoever is running the study at the end of the day. So it involves a lot of collaboration and may involve some complex non-disclosure agreements. And these studies are very time intensive. They take a long time to do. They take a long time to set up, and they'll take a lot of your resources and a lot of computational resources as well. So we have to plan for that. In our shop, we have a lot of highly capable machines. We call them Threadrippers. These supercomputer type things that are able to run a lot of cases at the same time and can run them quite quickly. But that's something you might want to think about if you're trying to sort of spool up these studies. Mixed SSR and SSCI interactions. We might see a combination of these phenomena in a study, which can make them difficult to isolate and analyze, and also to mitigate. And we also often have to consider a large number of potential operating scenarios. to figure out whether things are going to be stable or not. So that can increase the the scope and complexity of the study quite a bit. Okay, so I think the next thing I'll do is walk through a really nice example study on SSCI specifically. This was done by a couple of folks from my office, Anurada and Rachel. And I think they put some of this content together a while back for an industry forum. So feeling their work here. So in this scenario, we had a large PV plant and a large battery plant connecting in a hybrid configuration into a heavily series compensated configuration. This is what the network looked like, simplified version of it. So we had our project here. We have 4 lines going out, and they're all series compensated. So we were, there's a huge number of different resonances you can run into with this sort of configuration. The range of resonances was from 15 hertz to 48 hertz. It's a very high frequency series resonance. And this is a very, challenging project to study and to this isn't a great place to build a project, honestly, right? This is very much in the territory of you're going to be right on the limit of whether you're going to get this thing working, which is kind of what we knew going into it. So just some details on the plant. There was 3 equivalent feeders with 250 megawatts each, with collector systems, detailed, custom-tuned OEM PV inverter and battery inverter and PPC. The transformer neutral grounding reactors involved, arresters, transformer saturation, series capacitors with MOV and protection, and detailed transmission line models. So the first thing we did is the passive frequency scans of the system. And you can see 2 sort of plots here. We have a radial case and a near radial case, where in the near radial case, you can see that there's, like just in this plot, you can see that there's a resonance here around 14 hertz, a very pronounced resonance at maybe 26, and then another one at 46 or something. So we did these passive frequency scans for a range of 2 to 55 hertz. Series resonances were observed when we had a series compensated line is radial or near radial, of course. So we all kind of talked about here. If a generator is connected to a series compensated line parallel with other lines, then a dip in the reactance can be observed. So a generator can look like a parallel path for the impedance as well. So again, the dynamic frequency scan for the IBR side, the dynamic or active frequency scan, we take our IBR here, take a voltage source, and we add some voltage perturbation on it. That's this delta V, and then we have some current here, and we do an FFT of these 2 quantities and figure out the impedance characteristic. So these are the results of the frequency scan for this particular plant. And you can see this one in the top left here is the PV only scenario. And the resistance crossover point is like 32 hertz or so for that configuration. If we look at the battery only, we get something that looks like this, where the crossover, the crossover point is a much higher frequency. It's at 48 hertz, so it has much better damping profile, the grid forming battery compared to the PV. And if you put them both together in the system, you get something that's about halfway between, or actually a little bit closer to the 48 here. So you get 45 hertz as a crossover frequency if you scan them both together. So this is that's the same slide here. I presented already. We can combine the passive scans with the active scans, come up with the combined scans, and figure out what's whether it's going to be stable or not. This is the same plot. Both of these were unstable, as we looked at already. So we can do some just some impedance-based thinking about the effect of various network configurations on the resonance that we're looking at. And we have this. We know our resonant frequency is going to be a function of the inductance and the capacitance in the system, pretty much like this. So 1/√L times C. And so when we think about the inductance here of the system, when we decrease the inductance, this actually increases the frequency. So this means that if you have a stronger system where our inductance is small, you actually are more likely to see these resonances. The resonances move to higher frequencies, which will usually make shift the resonance to a worse damping location for the IVRs. So stronger system can actually make this phenomenon worse. So it's not related to it's not associated with a weak system issue at all. This is a stronger system actually make things worse in many situations. The second row here, adding more series compensation in series is going to drive this, make this C lower and drive up the resonant frequency as well. So that's another thing. You have a device that a transmission line that's 25% compensated versus 50%, you'll see that the resonance will shift higher the more you compensate that transmission line. And then the last one here, if you have more, let's say you have two paths out of your point of interest, and they both have series caps on them. If you bypass the series cap on one of those, or let's say it's initially bypassed and then you turn it on, you're adding more compensation in parallel, which will shift the resonance downwards. So this is a bit of a confounding. When you look at what the formulas, it's not that confusing. But what that means is that the case where all series caps are online is not necessarily the worst case, because you have multiple of them in parallel, which is increasing the capacitance and decreasing the resonance. So in this network configuration that we're looking at here, it's not necessarily the case that this when everything is on, all the caps are in service, that it's going to be the worst scenario. So another important part of the screening is to also toggle the status of the series caps, whether they're bypassed or not, as part of your network screening. So yeah, as I said, having all series caps in service does not represent the worst case scenario. It's going to be location and topology specific. The most severe resonance and highest negative damping generally occurs when the system is radial through a single series capacitor. So you have no parallel series capacitance paths. You have a single path out to the system, and it's a strong system behind it. And then that's generally when you'll get the most severe resonance and occurring at the highest frequency as well, which is not something that's super intuitive when you first look at these systems. Okay, so let's go through some of the results that we saw in this specific study, as they're quite interesting. In this scenario, we have only the PV in service, and when we test this specific N-3 condition, we see that zoom in here, a few interesting things, right? So first, you'll see the plant start to oscillate right after the fault clears and that line is taken out of service. You'll see the oscillation start to build. And then the plant trips quite quickly. So there's a fault ride through failure here, which the plant trips for. And after the plant is tripped, if you look at the voltages in the system, they're still oscillating wildly. And this is due to SSFR, the transformer, the main power transformer. So this is also, interaction between the transformer and the series cap with the IBR plant completely tripped at this point. So in this sort of thing is something to be aware of in these studies as well, that we can have ride-through issues which can mask the SSCI issue. So there it's sometimes it's useful to have the capability to just turn off protection in the model so that when you're running a study, you can, if you see, you run everything, you see the plant is tripping, like right at the fault clearing or something, you can, as a second step, you can go ahead and turn off protection and see whether there's going to be an SSCI stability issue if that protection event wouldn't have triggered. Again, all the cautions about changing parameters and model and disabling protections apply here that we talked about yesterday. So the conclusion from this was, that we should do tuning to. Well, it was a few things, right? So that there was a ride-through failure caused by the phase overvoltage. There was SFFR concerns, so it was recommended to install a subsynchronous detection relay to disconnect the transformer. And the plant's inability to ride through the faults masks the SSCI issue associated with the PV system. And the next one we tried was just the battery by itself. And this was totally fine with 750 megawatts of the battery online. It didn't trip here. There was a post-fault overvoltage, but it didn't disconnect the plant. It was able to ride through the event. So no SSCI oscillations. I think, if the plant would have been disconnected initially, then there potentially might have still been SSFR issues. So that recommendation to install the SSFR relay was still there. The next one here, detailed time domain results for this is now 750 megawatts of the PV plus the BESS, right? So now we're starting to combine the two together to see what the combination looks like. And here we have similar sort of thing as we saw before. Maybe it's able to, the PV plant was able to hang on a little bit longer, but ultimately we still see the PV plant, I think the PV and the BESS, maybe just the PV though, tripped. And then after the trip, we got SSFR again. So the same thing again with now 50% of grid forming BESS in service. And now we see a stable result, no ride-through issues, no SSFR, and no SSCI. So this was, this was really useful to know. So the conclusion was that to ensure SSCI stability, we need at least 50% of the grid forming batteries to remain online. And it was recommended to install a subsynchronous detection relay for SSFR. Further tuning of the PV inverters was recommended as well. The PV inverter firmware, I think there maybe was some firmware. Maybe it didn't have the right firmware in the study as well. So it was, other way around. It was recommended to update the inverter firmware to reflect the parameters of the tuned EMT model. So just make sure that the parameters from the model get into the actual equipment, right? And this specific study, there was other plants in the system which were not included in the study because we didn't have models for them. So, recommendation was to perform some cluster-based SSCI EMT study that included all the other nearby plants at some point in the future as well.
Question on that. Do you think, so kind of feeding this back into the model validation stuff that you guys had, do you think there would have been any additional value in maybe running various combinations of the hybrid plan. The PV only in service, the VES only in service, and then maybe at various output levels as part of the model validation.
Yeah,
On the front end as well.
for sure. Yeah. Yeah, we would definitely recommend that to try things at different dispatch levels and model verification as well. Not that, you can't do endless testing on all the combinations, but pick a few bookends and run those. Okay. All right. I think we're gonna maybe I'll see if there's any more questions on SSO, SSCI from the group and change topics. Okay, so next thing we'll talk about is large data center load study considerations. Just know there was some questions on earlier, and if there is anyone here who was at the last one, I think Andrew went through a lot of this, so I apologize for the overlap. Gonna dig into here. So I think we'll start off with just mentioning a few types of these large data center type facilities and just some specific characteristics of them, which are important to think about. First one here is just hyperscale cloud facilities. These are typically owned by cloud service providers, and they're they're companies like services like AWS, just offering cloud compute to whoever wants to use that. And they typically have a very, pretty flat load profile, I would say. The hardware in these facilities would be, cooling with a variable speed drive, sometimes with an active filter. IT infrastructure behind distributed power distribution, often behind a UPS. So these, they have usually some amount of reliability that they want to maintain for the compute that's happening there, and then they'll have lighting and admin computing and other small IT load like that, and then often they'll have diesel generator backup as well in case they lose the grid service. So these ones are kind of like what data centers have looked like, let's say in the past have mostly been something like this. And the next one here, crypto mining, purpose, of course, to calculate Bitcoin tokens, etc. They're typically owned by private developers, and cooling is usually by natural wind or forced air. They are using power supplies. They may not have a UPS. Kind of depends on what they're doing, I guess, and they may not have backup generation as well. Their load profiles are pretty flat, I would say, compared to what we're going to talk about next. But yeah, these have been on their systems for a while as well, so we have some understanding of what these look like. And the next one here, this is AI inference. So this is the purpose here of these facilities would be to, when you type a question to Gemini or something, that isn't a AI training. That's just a model that's already built, and it just has some amount of compute that it has to do to give you an answer. And for a given facility, it's going to be many users trying to get answers from Gemini at the same time, or roughly the same time, so they can distribute that effect over maybe multiple facilities. So we would expect relatively smooth profiles from a facility that's doing AI inference as well. These can range in size from hundreds of megawatts to like a gigawatt as well. So these can be really big facilities. Gemini, GPT, ChatGPT, etc. All these large load models are running these AI inference requests whenever you ask a question of it. The hardware is going to be similar to the hyperscale, but potentially lower reliability requirement. Like they might not be using a UPS necessarily. AI training is the last one here, and this is the, I guess the one that's created the most buzz in the industry in the last while here. So these are training major AI models for use in future use in inference. These are generally owned by private developers or hyperscalers directly. So you can have, various groups owning these facilities, and they can be, as we know, they can be really big. A lot of the ones that we are talking about are sort of in the gigawatt scale, and they're kind of popping up all over the country. So this is the one that's getting the most attention and is driving a lot of discussion, I guess, let's say. So these examples would be Microsoft, Oracle's, XAI, Amazon, and Meta's of the world. And the key feature, or the defining feature for these, would be the variable active power output of these facilities. And in terms of the actual hardware, these would be the same as the AI inference. So these are going to be power supplies, and there may be UPSs as well. So the large load characteristics, this figure here was taken from a paper that was published somewhat recently, I think. So you're welcome to look up the reference there and have a read. But this is an example load profile from a large load, or not just a large load. This is just at the GPU, from the GPU here. And you can see the variations that we're seeing here are obviously very large, and there's a fair bit of harmonic content in these fluctuations. There's various phases of cycling that's happening here. I'm not an expert on exactly all of them, but I understand that there's these dips that go all the way to near zero. 0.1, 0.2. These are when the GPU is sort of doing a data exchange with some central processor, and they're for that reason the compute goes down. It's not sort of actively training at that time, and then it starts to train. It ramps up, and then the training process itself results in these fluctuations here that we're seeing. And this process, what we're hearing is this is basically synchronized across the entire facility in large part. So these dips won't be occurring just, it won't be occurring at, time X on GPU 1 and time Y on GPU 2. Generally, they're sort of synchronized across the facility. Which is, I guess, what the training this I guess is the most efficient way to do the training, which is really the main priority for the large loads is to for these facilities is to train the model as quick as possible, and so that's their priority. And so that's kind of one concern. The other thing is they are not designed to ride through system events in most cases. And this is sort of a thing, if you talk to one of these load facilities, they might say, oh yeah, we ride through, but they might be talking about, they can keep their load online. So they can make their load ride through in a system event, but from the system perspective, they're not riding through, they're just going on to their UPS. So UPS doesn't count as ride through, right? Because the power drops from the system. It's no different than if the load had tripped to the system. And the loads themselves are a mix of converter-based interfaces. We can have the power supply units are generally they're like a single phase. At least the ones that we've seen so far, they're like a single phase unit, a switch power supply, switch mode power supply, and the UPSs might be might be a little bit have more of an active front end, let's say, and they might have different characteristics. So there might be a range of different power electronic devices in these facilities that we So let's talk about some of the basic reliability risk categories associated with these large loads. So the first one is just basic power flow considerations. Can you supply enough energy to meet this load? Or do you have enough reactive power in your system to meet this load? All these are things that are just things that can be studied with a power flow program and are just sort of steady state considerations. And of course, we have to maybe think about them a little bit harder because of how large these loads are. They're, if we're talking about a gigawatt, that's a massive facility. So we might be some extra considerations there. But active power variation, so synchronous generator damage, when we have these large and rapid fluctuations, those fluctuations can propagate onto the synchronous torsional shaft and cause damage there potentially. Talk about that in more detail. There might be flicker associated with these rapid fluctuations, and there might be machine mode oscillations that may be impacted, or inter-area oscillations. And then, of course, there may be a ride-through failure as well. So if one of these large, huge facilities trips from the grid, you're going to have an overvoltage due to the load rejection. And we have to think about whether the system is designed to be able to handle that overvoltage, and it may be like really big. And then some other considerations like resource adequacy and reactive adequacy for ride-through failure. The last category here, passive damping, so SSCI instability or SSTI instability. So very similar to the previous SSO conversation. These are huge IVRs on the system, effectively, or not resources, but inverter-based devices, let's say, and they can be susceptible to SSCI in the case of a series compensating system, or they might be destabilizing a torsional mode as well, just by nature of their damping characteristic, right? So power flow studies, again, we want to make sure sufficient generation exists. Careful with I guess your assumptions about what's happening in other places in terms of imports will handle it. Again, these loads everybody's getting hit with these load requests, so don't assume that energy is going to be available from somewhere else necessarily. You want to be able to serve the load under various outage conditions, of course. So again, just pretty standard project process that you would go through for a power flow analysis for some of these loads. You want to make sure that the VARs are available to control the load for various transfer scenarios, and that VARs are available for fast changes in the load as well. So some of these, of course, you can study in other domains, but you can get some idea of whether the VAR availability in a powerful program as well, if you just study different load levels and see whether the VARs are there and how much fluctuation there is in voltage and things like that. So just a brief reminder on the synchronous generator shaft. Talked about this a little bit, but the generator shaft might have many different turbines on it. So you have a bunch of different masses connected with springs and shaft sections, and we can get the information. Sometimes we can get the information about the masses and the springs from the manufacturer, and then we can put that through an eigenvalue tool to figure out the actual modes of the torsional modes that are on the shaft. And this is like, this is data that you don't necessarily get for every generator. They might not have given this to you in the past. And just to sort of when we're running like a normal a normal study in our transient stability study. It's not that we are assuming that there's no mass on the shaft or something. We just have all of these masses lumped as a single mass, which we can represent the inertia and things like that. But when we take that single mass and break it out to its individual elements, that's when we see these various torsional modes come into effect. So synchronous generator damage risk evaluation. This is something that we've been thinking about a lot in the last year or a little bit longer, I guess. EMT simulation is required to assess this, mainly because that these frequencies here that we're seeing here are they're happening at a frequency range where we know the phase domain studies are not valid at these frequency ranges. So we have to go to the EMT domain to study these impacts on the synchronous generator shaft. And we need that modeling detail from the manufacturer in terms of the shaft information. And the next one here, for the load profile, right? We have to make some sort of assumption on what sort of injection the load is going to be putting out onto the system. In operation, it's going to be whatever load process is running on it. And when you talk to the load vendors, they're quite hesitant. They'll never tell you that, hey, we're going to do exactly this profile with no variation. They're basically going to say this is like, roughly it's going to look something like this, and they might give you some indicators saying this dip might occur every second. It might occur every half second. It might occur every 2 seconds. But they'll give you an idea of the general shape, but they won't really commit to the, let's say, harmonic content of the profile. They might commit to a maximum amount of fluctuation. They'll say, there's some methods that they can use to limit the bottom of those variations to some level. But in terms of the harmonic content, what we're hearing is that it's very difficult for them to commit to, staying out of a certain frequency range, for example, or staying within some other frequency range. But that assumption on the load profile is extremely important if we're going to investigate the potential damage to a synchronous generator, mainly because that we know here what the mechanical modes are of the shaft, and if we start to hit this generator with power fluctuations that match up with these torsional modes, then we will excite a torsional mode on the generator, and we could very easily have damage on the shaft when we start doing that. So as far as we can we can tell, this is likely going to be a real issue, and potentially has been an issue in some places already as well, but maybe hasn't been well documented yet. And so let's say we have assumed, let's say we have the data of the shaft, and we have some assumed load profile, and we can then take our system model, we can put in the load, we can put in the generator, and play in the profile into the EMT model, and we can then measure the generator shaft torques and maybe some active power variations. And then we can compare that information against active power, let's say not active power, the SN curve that we showed on the previous slide deck there. You saw that it had the slope, right? So I'll go back to that slide here just to demonstrate it. So here, this is an example SN curve, and you can see that in this specific one, there's some bottoming out of this curve here, assuming it it just, will saturate. Like here, we're at, I don't know, what is this? We're like at 1 million cycles or something out here, but keep in mind that these loads are not, they're doing this 24/7, so, and multiple times a second, right? So this is, 1 million cycles is nothing. This is, you can assume infinite cycles effectively from these load profiles. If they were doing something problematic, you might as well assume that it's infinite, because it's not like event induced or something. This is just like a forced oscillation that they're pushing out onto the system by nature of the software process. There's no, it doesn't really depend on the damping of the system. It's not really a damping problem. It's going to push out this power regardless of what the damping is. And if we end up in a certain network configuration where we're a lot of that power is shifting, being supplied by those power variations are visible to the synchronous machine, then we can have torque impacts. Shaft impacts. Okay, so this is sort of a perfect world process that we would use to evaluate these risks. Like, so as I said, a lot of this data isn't available, and the load profiles, the loads are, you can't really pin them down to a certain profile. So we kind of have to make some, in practice, we have to make some, where we are right now, we're making some pretty worst case assumptions about the profile, right? Which we can talk about in the next slide. But if we can't pin them down to a certain profile, we have to assume something for the study. So we can compare fluctuations from a certain profile against the machine long-term capabilities. And what we hear is that the SN curves are maybe not the only thing that dictate the impact of these fluctuations on the machines. There might be heating effects that are not captured in the SN curves. So there might be more impacts than what we know about on them, and the machines are, they're to come up with those SN curves is quite an arduous process involving finite element analysis of like the materials involved in the shaft, and things like that, and it could be various other things that might break at some point in the machine as well that maybe they don't know about. But so they're, the machines are also kind of cagey about, the machine OEMs are kind of cagey about committing to a certain level of torque impact, which they can say that would be no damage. It's kind of hard for them to commit to right now. So these are challenges. Data required, again, talked about these. You need a detailed grid model as well. And I'll say the alternative here, right? So if you're doing a detailed study and trying to figure out the impact of this load on this generator, this is the kind of information you need. If you have like a blanket requirement on the load fluctuations that are allowed in the system, then your job gets a lot easier. You can just say, you have to stay within this band. If you can't, then you can't connect, right? It's as easy as that. Now the band that you choose, of course, should be probably well informed on the impact that it might have on your system. If you choose a band that's too big, then there might be damage that might occur, that you basically didn't set your requirement tight enough. And on the other hand, if you make your requirement too tight, basically no one will be able to meet it, and nobody can connect, which is, maybe that's what we have to do, but it's something to think about. So we did some example study work for ERCOT in our shop, where we took a small sort of test grid, and we call these systems a toy system, because it's not representative of anything real, and it's very simple and easy to play with, but we can test a lot of different things in it. And what we did here is we just, we have if I zoom in here, we have an infinite grid and connected to a synchronous machine, and then connected to a load, right? So there's a grid, there's a machine, and there's a load. and we can play with the grid impedance, and we can play with, the load profile is basically what we're doing here. The machine has some torsional load at 12 hertz. So we've made up some multi-mass data for this machine, and we put it in, and we calculated the eigenvalue to be 12 hertz torsional load for this machine. And the next thing we did is we played in a variety of load profiles into this load. And this is not a particularly sophisticated load model, right? So it wasn't a power electronic model interface at all. This is like literally just a variable resistor. That's really, to study this specific phenomena, you don't really need anything more than that. And the type of load profiles that we played in were one of two. So it was a fixed frequency square wave that was just a up and down square wave at a certain frequency, varying between 25 megawatts and 100 megawatts, with some ramp rate applied. So we know that the loads they're not stepping, instantaneously. There is some amount of ramp rate that's visible in there, the way they're moving up and down. It's about, we've seen a few profiles, and we think this 10 megawatts per 1 millisecond. This would be in per unit. So 0.1 per unit in 1 millisecond seems to be a reasonable ramp rate, but this might change load to load, might change DPU to DPU, and might change collector system to collector system as well, a little bit. So, okay, so that's one profile, just a square wave, right? The next one would be a proxy waveform, roughly mimicking the measured AI training load profile. So basically taking something like this figure here and just converting this into actual raw data and playing this characteristic repeatedly over and over again into a variable resistor. So those are the two kind of profiles that we looked at for this investigation, and that so the first like scenario 1 and scenario 5 here. This is load profile 2, so the square wave at two different frequencies. So an off torsional frequency of 2 hertz, and then the on torsional frequency of 12 hertz. And when we did that, we measured a few things. We measured the load fluctuations. These are steady state numbers, so they're not going to exactly like line up to the amount of load fluctuation that we're pushing exactly, and there's kind of reasons for that. But just be aware, these are like, if we keep doing this for a long time, what do the values settle out at? Which is kind of what we're assuming for the study right now. It's different than the initial transient. But so, just for these first two, we're looking at a certain amount of load fluctuation, a certain amount of fluctuation visible at the machine, and then a certain amount of fluctuation going into the system. And we can tabulate the amount of torque that we're seeing on the various shaft sections for these two instances. So load profile 1, the square wave at 2 hertz. So the off torsional, we see still some torque impact, right? So it's like 0.2 per unit or so. And that 0.2 per unit, that might be still enough to cause shaft damage. We don't really know the answer to that right now. But there's two main reasons. The main reason is really that when we're applying like a load step that doesn't just have 2 hertz in it, a step has many other frequency components in it. It has actually all frequency components in it, and some portion of that is 12 hertz or around 12 hertz. So we are getting some amount of 12 hertz component into the shaft, even if our square wave is moving at 2 hertz per se. So the next one is scenario 5, load profile at 12 hertz. So this is really just the worst thing we can do to the machine, is to just vary exactly at the torsional frequency. If we do this, the shaft torques will quickly grow to like 5 per unit, and this shaft would have broken very quickly if this would have happened in reality. Scenario 9 here, load profile 2. This is again, the proxy waveform, kind of as directly as we see it from the paper, with nothing sort of like added in or modified. When we run this, we see pretty low torque components on the shaft. But again, the load profile isn't going to tell you that we're going to stick exactly to that profile. So, but what we did is we took that profile and we injected a little bit of 12 hertz component on top. So we added, I think, 5% or 5 megawatts of 12 hertz component, and we sort of perturbed that load profile with a little bit. And we added it and then we removed it, and we'll show you what that looks like. Now, when we did that, even just that 5 megawatts of 12 hertz component was enough to get up to like 1 per unit torque impacts, right? So this, yeah, these are the kind of results we had. We can look in a little bit more detail as well, but just note that this phenomena is very sensitive to to the various impedances that are in this network. So if we just imagine no oscillation or anything like that in the load, let's just apply some change in load over here, and that change in load will need to be split between the grid and the synchronous machine, and that split will be determined by the impedances. So if this grid impedance is very small compared to the impedance to the synchronous machine, then most of that load fluctuation is going to move into that grid. It might be a problem for other machines in that grid, right? So the power fluctuation has to end up somewhere, but maybe it's distributed amongst enough machines that it won't be a problem for those. But if we have the other way around, if the grid impedance is high and the synchronous machine impedance is low, then that power is gonna, rather than going to the grid, those fluctuations are gonna hit the synchronous machine instead. And yeah, so so let's look at the set of results here. So this is that load profile 2 with the 12 hertz component added in, perturbed on top. So this is the load profile that we played in. Basically looks like this, very much like the paper, except at these where it's high and was already oscillating a bit. We just added some more oscillation onto there. We added the 5% at 12 hertz component into that load profile. And the synchronous machine active power is absorbing a lot of that power, not all of it, but a good chunk of it. And the active power from the grid is basically doing the rest. And you can see that, yeah, there's a lot of harmonic content showing up at the synchronous generator, and some of that is that dangerous 12 hertz. And then on the right, we've plotted the torque on the various generator shaft sections here, and you can see it's where that 5 hertz component, as I said, or the 12 hertz component, where we're putting it in and we're taking it out, according to this plot on the bottom here. So when it's when we put it in is where we see this growing up to near 1 per unit, and then if we take it out, it basically goes down and settles again, and then comes and goes as we take that component in and out. So this is a pretty good sign that this was a good indicator, let's say, to ERCOT, that this is could be a real problem for certain network conditions and for certain load profiles. This could definitely cause damage on synchronous shafts of synchronous machine. Okay, so some additional study challenges here. So data is very hard to get for the load. There's there's various amounts of data that we might be interested in getting, right? So limits on load variation is a big one. We talked about the harmonic profiles of the load, not just at the subsynchronous, but also at also add actually the harmonic, at the, third harmonic, fifth harmonic and things like that. We're often very interested in knowing whether it's going to be a harmonic problem on the system. So that information is also difficult. Getting detailed models to quantify damping. All right, so this is a very important one because these models do not exist today. We don't have models from the OEM vendors that are of sufficient detail to assess the damping from these loads. They're in progress, I'd say, and maybe in a couple of years we'll have reasonably good models for these UPSs and power supply units, things like that. But today they don't exist, but they're working on them. So yeah, we'll see where this goes. But at this moment, we don't have a good way of assessing the damping that the load may or may not be providing to the system. So we can't really study SSTI in terms of the damping characteristic, and we can't really study SSCI right now either because we don't know what the damping characteristic is going to be like. The early indicators are saying that the damping characteristic of the power supply units is pretty good because there's not a lot of very active controllers on those devices. They're kind of just rectifiers for the most part. So there's the resistance profile looks pretty good from what we've seen. Yep.
We look at it, I think all the information's there to think about it from the other direct perspective, which is, you're looking at from load impact on the system. Can we say, here's the system limitations and basically prescribe your design must be able to, not impact these modes. So in other words, instead of treating it like an unknown, we're saying you need to design your equipment in this fashion. I think all the elements are there to be able to be prescriptive in the other direction.
Yeah, I think that's definitely something that is possible to do as well. I think the designing. I mean, I think it's a question of speed. Like, there's a lot of momentum into getting these things online very quickly, right? So, and this design, like, a lot of these like power supply units are they don't have a lot of capability baked into them right now, and these OEMs who are developing them really have to put a lot of research and development into improving the characteristics before we would see, for example, like better ride through, or if there is a resistive or damping problem to fix that. So they're not like at the same level that the IBR manufacturers are at all, right? They're like where the IBR manufacturers were like, I don't know, 20 years ago or something, right? Because they're just starting off. So
what forces it is putting requirements on it that they have to go figure out. I know it slows it down, right? Everything's moving at warp speed, but I mean, the risks are damage to really significant equipment, right?
Yep.
So, yeah, honestly, I've been searching for a way to cause them to pump the brakes, and this kind of sounds like a way to kind of help.
It's a really good point. Yeah.
I guess kind of on that same note, are the frequencies, so theoretically, like you're talking about, say, a battery inverter system locally, similar to UPS, but to absorb the transitions of charging the charge discharge cycle to line up with the power consumption to level it up, right?
Yeah. So
is that I guess that's kind of getting into grid forming inverter stuff a little bit, but then I think it should be sort of helped out.
yeah, like we'll talk a little bit about like mitigation, I think a little bit later on, but there's things you can do to mitigate on the DC side and on the AC side. It's kind of the same question of, if you're asking the power supplies to innovate, it's going to take a while. They can do it, but it's going to take a while to do it. But So we're kind of like in a bit of a little bit, we're in this in between time where we're trying to patch things based on anything we can, right? Whether it's East Adcoms or whatever.
It's far enough. Fill that gap. a little
Yeah.
bit, too.
Yeah, it's a good question. It's a question of like speed of response and whether you're able to connect close enough to that point. But we'll talk about it a little bit more as well.
And then there's-
Yeah, they'll pay for it. All right, I think